Okay, this is a recording of the 2-4 worksheet. We're starting out with problems in which they ask you to find the average rate of change of a function over an interval. Anytime you think of average rate of change, I think it's best if you think of it in terms of rate equals distance equals rate times time. So in other words, if I want to find the average rate of change, I find the total change in the distance traveled divided by the total time that was traveled. It's the same thing with the function. We want to find the total change in the y value over the total change in the interval. So in this case, it's f of b minus f of a all over b minus a. It's the slope formula. That's all it is. A rate of change is the slope formula. The average rate of change is the slope formula. So if we plug 2 into that, we get out 3. If we plug 0 into f, we get out 1. 2 minus 0, so we get 2 over 2, which is 1. Okay. The b portion of this, you just get an irrational answer. That's okay. We're going to get lots of irrational answers throughout the year. So we need to expect that. So for b, it's the same idea. Part b, f of b over minus f of a all over b minus a. So the square root of 49 is 7, but the square root of 41, we just have to leave it as the square root of 41. This is all over 2. 12 minus 10 is 2. Okay. Problem number 2. So problem 4 is again asking for the average rate of change. This time the interval is from 1 to 4. So it's f at 4 minus f at 1 all over 4 minus 1. B is always the right endpoint of the closed interval. A is always the left endpoint of the closed interval. The smaller value is A. So natural log of 4, here's the function. So natural log of 4 minus natural log of 1 all over 3. Make sure that you know that the natural log of 1 is 0. Remember, a logarithm says, what does the exponent have to be in order to produce this number? Well, it doesn't matter what the base is. The exponent has to be 0 to produce a number of 1. Any base raised to the 0 power is 1. Therefore, the natural log of 1, or the log of 1, or the log base 2 of 1, any logarithm of 1 is always 0. We have to recognize that right away. So it's really just the natural log of 4 over 3. I also wrote it for you this way because frequently on a multiple choice problem it would be written this way. Remember that 4 is 2 squared, and I can drop down the exponent of the argument and make it the coefficient of the logarithm. 2 natural log of 2 over 3. Part B of this question is just another irrational situation because of the natural log. So it's the natural log of 103 minus the natural log of 100 all over 3. The only thing that I did here is the 1/3 can be pulled out front. Same thing as dividing by 3. And I could compress these two together. If I'm subtracting natural logs, I can write it as 1 natural log and divide the argument. So that's what I did on that problem. Problem number 6 is also asking for the average rate of change. On this one, now we have a trig function. So we're just getting used to evaluating a variety of functions here. That's it. The interval, again, is given here. So b is pi and a is 0. So f at b minus f at a all over b minus a. What I did draw for you is the unit circle so that we remember that the cosine of a quadrantal angle equals the x-coordinate of the unit circle. The sine of a quadrantal angle equals the y-coordinate at the quadrantal angle of the unit circle. And the tangent's always going to be sine over cosine, so it's y over x if we have to evaluate a tangent. Here we're just evaluating cosine, so it's 2 plus the cosine of pi minus 2 plus the cosine of 0 all over pi. Cosine at pi is the x-coordinate at pi is -1, right there. The cosine at 0 is the x-coordinate at the angle 0, which is 1. A lot of people will put 0 here. That will be on the AP test frequently. That the cosine of 0 is 1 and that e raised to the 0 power is 1 because students have a tendency to make that 0 when they shouldn't. Okay, so this becomes a 1. I'm subtracting 3 all over pi, and I just leave my answer -2 over pi. Very common for us to get answers like that. Here's part B of the particular problem. This time we're going from pi to -pi. So f at b minus f at a all over b minus a. Notice this is minus a negative, becomes plus a positive. Pi plus pi is 2 pi for the bottom. But again, I've got to plug pi in. Pi is the same as negative pi, the same terminal angle, same terminal side. So it's not the same angle. Positive pi comes this way, negative pi comes this way, but we end up at the same location. And the cosine of both of these is -1. So we get 2 plus the cosine of pi, 2 plus -1. I'm subtracting 2 plus the cosine of negative pi. This one was positive pi. But in both cases, we get 1 minus 1, and that is a 0. And 0 over 2 pi is 0. We can get an average rate of change of 0, just like we did in this problem right here. For this next problem, they want us to estimate the slope of the line segment drawn from point P to point Q sub 1, then from point P to point Q sub 2, point P to Q sub 3, point P to Q sub 4. In the book, they wanted you to approximate it. They did not give you the coordinates for these 5 or these 4 points Q sub. I just gave you these values, so all of our answers will match. Okay, and point P we can clearly tell is 1080. These other ones, if you look at it, makes sense. The point Q sub 1 is 520, point Q sub 2 is 738, and then I estimated these here using the same values that they did for the solution manual in the book, by the way. Okay? So we're just doing the difference quotient. This is definitely going to be on the AP test, just the difference quotient. Just knowing the slope formula is definitely going to be a situation that pops up on the test in several different locations. Even once, for sure, on the free response. So I'm just subtracting. I'm subtracting from point P to point Q sub 1, subtract the y's over subtract the x's. We get 60 over 5, or a slope of 12. I'm doing the same thing, except this time I'm using point P with the coordinate point that I set up here for Q sub 2 right here. So this time 80 minus 38 over 10 minus 7 is 42 over 3, which is 14. The slope seems to be getting steeper. And if you look at that, it would make sense. If you connect those two dots in the picture above, it would make sense that the slope is getting a little bit more steep as we go. So if we subtract for this one, 80 minus 56, because now I'm using this point, over 10 minus 8.5. Well, that's 1.5, and it's best to write it as 3/2, because if I multiply by the reciprocal, 24 times 2/3, 24 divided by 3 is 8, 8 times 2 is 16. We should be able to do that without writing a whole lot down to get 16. What about this one? 80 minus 72 over 10 minus 9.5, same thing. We get 8 over 1/2. Multiply by the reciprocal, we get 16. So it looks like it's starting to zoom in on a particular slope. So then it says, can you predict what the speed will be at point P? Well, it's going to be pretty close to 16 meters per second, because Q sub 4 is pretty close to P. Now, maybe you said 17 meters per second because you thought, well, it's probably getting a little bit more steep. That's okay. It's just an estimate. And it also asks for the units of measurement in this problem, which is meters per second. So we're getting closer and closer and closer to finding the exact rate of change at point P as point Q gets closer to point P, just like with that limit definition of a slope that we talked about in section 2.4. Speaking of that limit definition, here it is. So now we're getting into problems in which we want to find the slope of this curve, not a line. So we can't just use the difference quotient or the slope formula by itself, but we have to take the limit as h approaches 0 of the difference quotient. So you have to know this. This will not be provided to you, that the slope at any point A is the limit as h approaches 0 of f of a plus h minus f of a all over h. I will say it frequently. In this case, a is 1. So if they tell you to find the slope at a particular value of x, we might as well plug that in for a and not leave it abstract. I want to find the slope at 1. That's the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. So 1 plus h is coming into the f function, both here and here. Bracket the f of a plus h part, and then subtract and bracket the f of a part. So we make sure that we plug it into both parts twice, okay, and that we get everything plugged in correctly. That will help. Because now it's just algebra. FOIL that, distribute the negative 4, evaluate this, and we get this. When we FOIL, you get 1 plus 2h plus h squared. When you distribute negative 4, you get negative 4 minus 4h. 1 minus 4 is negative 3, but minus a negative became plus a positive 3. This is the beautiful thing about this. Every term that doesn't have an h must cancel every time. So 1 and negative 4 is negative 3, and a negative 3 plus 3, all of the constant terms go to 0. Every other term has an h. We might as well add these two terms together because they're like terms. 2h minus 4h is a negative 2h. So I combine those two terms. Notice I'm still writing my limit notation down as I simplify. You do not eliminate the limit notation until you plug 0 in for h. I still can't do that. If I plug it in, I get 0 over 0. So I factor out the common factor of h in the numerator. Remember, we never cancel terms and factors in the same step. You have to factor this h out front and show it being canceled. And now we can take the limit. We plug 0 in for h. When I plug 0 in for h, negative 2 plus 0 is just negative 2. That means the slope at 1 is negative 2. This problem asks us to do two things. To graph the tangent line and the normal line. So first of all, let's start with the fact that I'm going to graph the parabola first. I plotted some points here for this parabola so you can see it. You can find the vertex a couple different ways of this parabola when you're graphing it. You can stumble upon it by graphing it. You can do negative b over 2a to find out where the x-coordinate is. You also know that the vertex of a parabola is halfway between the two zeros, the two x-intercepts. So you want to find the x-intercepts halfway in between, you know that has to be the vertex. But plot some points, graph the parabola. To find the equation of the tangent line, we know that the slope of the tangent line is negative 2 because the slope of the tangent line equals the slope of the curve at the point of tangency. A lot of times the most complicated part for students is finding the y-coordinate of the point of tangency. Just plug 1 into the original function. If you plug 1 into the original function, you get negative 3 out. That slope through that point slope formula, or better yet, you go right to linearization. Y-coordinate plus the slope times x minus the x-coordinate. Distribute. Negative 2x plus 2 and a minus 3 is a negative 2x plus 1, or minus 1. That is the tangent line. We'll graph it here in a minute. Remember, the normal line is the exact same thing, except you're going to take the opposite reciprocal of the slope of the tangent line. Because normal line means perpendicular. The point of tangency is the same as the point of normalcy. So now this time we're doing the exact same thing, except we're using 1/2. So the y-coordinate of the point of normalcy plus the slope times x minus the x-coordinate of this point of tangency. Distribute the 1/2. Add these like terms together. Negative 6/2 minus 1/2 is negative 7/2. Please don't write this as a mixed number. We never write the slope as a mixed number, so we want to remain consistent throughout any equation of a line. So lines, we typically use improper fractions, not mixed numbers. Good. There's the normal line. Then come up and sketch those two lines showing that they are perpendicular at this point of tangency. You can just start at the point of tangency and count the slope out to graph it. That's the easiest way to do it. Just count the slope. Okay? Problem number 12 is essentially the same situation, same directions. I'm going to go through this one a little bit more quickly. The slope at 0 is the limit as h approaches 0. We can plug 0 in for a right away. Instead of saying f at a plus h minus f at a, we plug 0 in for a because we're only interested in the slope at 0 in this particular problem. And anytime it's at 0, it makes it significantly easier because 0 plus h is just h. So f at h minus f at 0 all over h. Notice I still bracket f at h minus bracket f at 0. This becomes minus a negative or plus a positive. The ones cancel. Never cancel terms and factors in the same step. Factor the h out front so that we can cancel the h. Plug 0 in for h and we get a slope of negative 3. So the graphical portion of this becomes a little bit more complex because now where is the vertex? I show the work up here. If you need to pause it a little bit longer so you can write it down, you can. But it's negative b over 2a. I plug that. b is negative 3, a is 1. We get 3 halves out. The only way to get the y-coordinate of the vertex, though, is then plug 3 halves back into the function. I show the work right here, and you get negative 13/4, or negative 3 1/4. So I'm going to the right 1.5, down 3 1/4. That's where my vertex is going to be to get a nice, accurate graph. But then I can just plot points to the right and left and get the idea of this parabola. Okay? When I'm finding the equation of the tangent line, I'm going to show that work right here. Okay? So the equation of the tangent line, remember the slope of the tangent line is the same as the slope of the curve at 0, which was negative 3. To get the y-coordinate of the point of tangency, you plug the x-coordinate into the original function. If you plug 0 into that function up at the very top, you get 0, 0, negative 1. That's why the output's negative 1. Here is linearization form. Y-coordinate plus the slope. Anytime the slope's negative, you might as well just say minus that. Okay? Times x minus 0. You don't even have to put x minus 0. Just the x is fine. Here is the slope-intercept form. The normal line is going to be the exact same thing, except I'm going to take the opposite reciprocal. So the slope of the tangent line is positive 1/3. Point of normalcy is the same as the point of tangency, but I have to run it through this again. Okay? Y-coordinate, this time plus the slope times x minus 0, which is really just 1/3 x minus 1. That's the normal line. And then we graph it. But again, once the parabola is graphed and you know the point of tangency, just count the slope out. The slope for the tangent line is up 3, back 1, up 3, back 1, because it's negative 3. Use a straight edge to draw it. And the slope of the normal line, which is perpendicular, is up 1 over 3, up 1 over 3. Draw that. There's a nice perpendicular situation. I only gave you one of these problems because there's an easier way to deal with this once we get beyond this chapter. But this is still good practice on using the limit definition of a slope of a curve at a particular value of x. And I gave you one where it was 0, so it really works out nice and easy. The very first thing that you want to do, though, we have to check to make sure that we have continuity before we even try the problem to see if it has a slope at that point. And the key is that it's breaking. We have this line that has a negative slope, and then it becomes this parabola. And what we want to know is it a smooth transition from the line to the parabola? What we first have to make sure is it continuous. So remember our definition for continuity. The limit as x approaches 0 from the left of this function. Does that equal the limit as x approaches 0 from the right of this function? And does that equal f at 0? Well, if I plug 0 into the top, I get out 0. 0 into the bottom, I get out 0. It's defined by the bottom. So yes, they are all 0. Therefore, this function is continuous. Once I have established continuity, now I have to do my limit definition twice. Once for the left-hand side, once for the right-hand side. Here it is to the left. The limit as the slope at 0 from the left. is the limit as h approaches 0 of f of h plus 0 minus f at 0 all over h. But I'm using this function because that's the left-hand defined piece of this function. That's why we always write top to bottom is the functions established left to right. Okay? So h plus 0 is just h. So plug h into that function. Remember, the function is just negative x. So I get negative h minus 0 over h. I can cancel the factors of h, which means the limit as h approaches 0 of a constant, negative 1, is just negative 1. We should have known that the slope is negative 1. It's a line. Of course, the slope of that line is negative 1. But I still want you to run it through this. I could give you more complex functions, but I'm going to give you some linear situations, so you're just verifying that this limit definition works even for finding the slope of a line. But then you have to find the slope at 0 from the right. And this time we're using the x squared minus x. The bottom piece of the piecewise function defines the right piece of this graph. So again, h plus 0 is just h. If I plug h in to this function, I get out h squared minus h. If I plug 0 in, I get out 0. So we have something that looks like this. Notice how I'm indicating 0 from the right with the plus sign. So I read this, the slope of 0 from the right. Factor out an h, cancel the h, plug 0 in. We also get out negative 1. If the left-hand slope equals the right-hand slope, then that is the slope at that point. If they are different values, then the slope does not exist, and we're going to find out that then the derivative doesn't exist. Okay? So this is important. There's going to be an easier way to check this later rather than having to do all this detailed limit work. But for right now, it's very good for you to know that we have to check the slope from the left, the slope from the right. So yes, the slope at x equals 0 is negative 1. And here's our justification, just like we justify a limit. The slope at 0 from the left equals the slope at 0 from the right. They're both negative 1. Here's a quick sketch of this just so that you can see. This line is coming down. At 0, it's changing to this parabola. I've graphed for you. And it's a smooth transition from this line to the parabola, which means the slope is defined at that point. If this line would have gone this way, for instance, if it was just y equals x instead of y equals negative x, this point would be too sharp and we would not have a slope. Those points are called cusp. We will discuss those more in chapter 3. On problem number 20, the best part about problem number 20 is the fact that now we're going to find the slope at some arbitrary value a. It's the exact same thing that we've been doing, except now we just leave a here, here, and here. We don't have a particular value. It's an arbitrary constant. So I'm plugging in a plus h right here. I get out 2 over a plus h. Plug a in right here, I get out 2 over a. How you simplify this complex fraction is up to you. I like to think of this h as being h over 1. So what factors appear in any of the denominators in the numerator and denominator of the complex fraction? A and an a plus h. So I'm going to multiply all 3 of these terms by a times a plus h. If I multiply this fraction by a times a plus h, the a plus h is going to cancel. I'm left with 2a. If I multiply this fraction by a times a plus h, the a is going to cancel, and I get negative 2 times a plus h. But I can't forget to multiply the h times a plus h as well. And if you do that, you get something that looks like this. I multiplied the 2 fractions on top in the numerator and the h all by a times a plus h. It's the easiest way to go from complex to non-complex. I will always do it that way, but you're more than welcome to make this all one fraction multiplied by the reciprocal if that works better for you. Distribute the negative 2. The same rule is going to apply. Every term that does not have an h must cancel. 2a and negative 2a cancel. Never cancel terms and factors in the same step, so I draw this arrow back up here before I cancel the h's out. But never cancel terms and factors in the same step. Once that h is canceled out of the denominator, the next step is going to be to take the limit by substituting 0 in for h. A times a is a squared, so it's negative 2 over a squared. That's it. This is nice because now I can find the slope at any value of a. If I want to find the slope at 1, it's negative 2. If I want to find the slope at 2, it's negative 2 over 4, or negative 1/2. I can find the slope at any value that you want to put in for x equals a. Okay? So this actually gives me a slope generator for any value of a. Same thing for 22. This particular curve on this one is another parabola, so this one is actually easier. You don't have the complex fraction. There is a complex fraction on the 2-3 quiz. Hint, hint. On this one, doing the same thing. A plus h minus f of a all over h. So remember, a plus h is coming in right here. And then when I subtract f of a is coming in right there. I bracket the front and bracket the back. That helps keep everything in order, because I have to FOIL this and distribute the negative sign. In all likelihood, I did it in one step. Okay? So it's 9. When I get a squared, make it negative. I get ah is 2ah, distribute the negative. I get h squared, distribute the negative. Distribute, distribute. Every term that does not have an h must cancel. A squared, negative a squared cancels. Negative 9, positive 9 cancels. There are 2 terms left. They both have an h. The next step is to factor that h out front and cancel the factor of h in the denominator. Once h is canceled out of the denominator, just take the limit. Plug 0 in for h. Negative 2a minus 0 is negative 2a. There it is. So the slope of that parabola when x equals 5 is negative 10. I can find any of them just like that now that I have the slope generator. 2 left. This is the same type situation. Find the instantaneous rate of change is the same thing as the slope. So I'm finding the slope. This time it's at 3, so I can plug 3 in right away for h. If you want to leave it a and do it that way, you can. It's just more abstract. If I plug numbers in, it's easier to deal with the numbers. So I plug 3 plus h in here and here. I bracket it. Plug 3 in here and here. Bracket that. Multiply everything out by FOILing and distributing. Distribute. Get these numbers together. Remember, this is 27 plus 6. Looks like it's going to be 33. Okay? So I show it in a couple steps. I FOIL first and distribute. Then I distributed the 3. You can multiply it all out in one step. It's fine with me. 27 plus 6 is 33. Every term that doesn't have an h must cancel. 27 and 6 is 33. Minus 33, all the constant terms cancel. All the numbers cancel. So now I can factor an h out of every term that's left. First, I got the 18h and the 2h together and made that 20h. So then I could factor the h out and cancel that h out of the denominator. That's the key. Once h is canceled out of the denominator, now we can substitute in 0 for h and get a slope at 3 of 20. Therefore, the instantaneous rate of change at t equals 3 is 20. So we can use this to find the instantaneous rate of change of functions, perhaps that are describing a position at a particular time. Now, there's going to be an easier way to do it, but this works out. Last problem, then we'll be done with this worksheet. At what points is the tangent horizontal? If we have a horizontal tangent line, that means that the slope of the tangent line is 0. Well, I got to find out what the slope is at any value of a, and then I can set that equal to 0. So what is the slope generator for any value of x called a? Okay? So the slope at a, again, is the limit as h approaches 0 of f of a plus h minus f of a all over h. You have to have this memorized. Okay? But remember, it's just the difference quotient. It shouldn't be hard to memorize it. When I plug in a plus h, now be careful, it's coming in here and here. That's why I bracket this entire front part. Then a comes in here and here. I bracket that all over h. There's a lot of multiplying that's going to get done, and I did it all in one step. I distributed the negative 4. I FOILed this out and distributed the negative sign at the same time because I think you are great multitaskers who can do the same thing. Here, I distribute the negative sign, negative 3 plus 4a plus a squared. Every term that doesn't have an h must cancel. Show the canceling of those terms. If you have a little marker or a pen, all the better. Every term that's left has an h. Factor an h out of all of those terms that are left so that we can cancel the factor in the denominator. Plug in 0 for h, and I'm left with negative 4 minus 2a minus 0. I don't have to put that. So the slope at any point a is negative 4 minus 2a. A lot of students want to plug 0 in for a. Don't do that. A horizontal asymptote occurs when the slope is 0. Set my slope equation equal to 0. Add the 2a. Divide by 2 when a equals negative 2. But it wants the point. Okay? So we have to plug this back in to the original function. F at negative 2 is going to be 3 minus 4 times negative 2 minus negative 2 squared. Okay? So I plugged it back into that function up at the very top, which is going to be 3 plus 8 minus 4. 11 minus 4 is 7. So the point is negative 2, 7. Now there's one in the examples just like this. And what I told you is this is the vertex. You should know your answer by doing negative b over 2a, finding out this before you even start this problem. But you need to verify it that this slope generator is going to find it for us as well. Because as these functions become more complicated, we're still going to set the slope generator equal to 0 to find horizontal tangents, even when those horizontal tangents occur at more complicated functions than parabolas. All right, I'll put these solutions out there. Hopefully everybody does well, and we can move on to chapter 3, which is even better.